Now we know that a charge can have a force exerted on it by an electric field. Or we can think about that in terms of this new idea, electric potential or voltage. So what if we apply one of these electric fields or potential differences to a material that might contain some charges? For example, a metal is a good example. Metals have the property of having lots of free charge that can move inside them. So this piece of metal here, we could imagine making at one end is essentially positive, and at the other end essentially negative. We'll talk in a while how we might do this, but for the moment we're just going to make one end positive and one end negative. That tells us at this end, at the positive end, we can think of as having a high potential, or if you like, a higher voltage than the other end, which we can think of as having a low potential or a lower voltage. What will happen now is that any positive charge that was in this would feel a force from the high potential to the low potential, and it would move along there. And we call this motion of charge moving along an electric current. And we give it the symbol capital I. And we say that the amount of current we have is how much charge has moved, the amount of change in charge, over how much time it took to flow. And we might say in this example here, we'd indicate that current is flowing along in the direction from high potential to low potential. Again, there's a bit of a confusion here because we're talking about positive charges moving. The direction of the field is defined by positive charge. High potential to low potential is defined by that. It turns out that in metals and most other materials that carry electricity, it's actually the electrons that move. We have to kind of forget that sometimes and simply concentrate on what we call the direction of current. So it turns out that positive charge moving in one direction gives us the same effect as negative charge moving in the opposite direction. Now, an analogy that's really useful here is to think about water flowing through a pipe. Here we have some object moving under the influence of some force. In this case, it's the flow of water rather than electric charge. And the force here isn't the electric field. The force here is from the gravitational field. And so our water is flowing through the pipe in much the same way as electric current flows through our conductor. And the height of the hill tells us something about the change in gravitational potential energy. So that height is kind of analogous to the change in electric potential energy, the voltage. So later on when we're talking about circuits, which we'll do soon, we're going to keep in mind voltage tells us about how much push is going along, current tells us how much flow is occurring. Now, we can take a source of voltage difference. We'll take a battery, for example, here at the top of the screen. This battery has the chemical property of providing a positive end and a negative end. And we can join that battery up to our conductor here. And that will basically provide an electric field throughout the conductor. So we might have a particular voltage, a particular potential difference this battery can provide, and what will happen is that current will flow from the positive around through our conductor and back into the negative. A certain amount of current will flow there. And we could go away and do some experiments here where we vary the voltage and see how much current we get. And it turns out that the more voltage you apply, the more current you get, as you might expect. But it also turns out that how much current you get depends upon some properties of the conductor, the material that it's flowing through. So it might have to do with the size of the conductor, it might have to do with the length of the conductor, it might have to do with the material the conductor is made from. But from the experiments you would find that the voltage that you apply divided by the current that you actually see flow turns out to be constant for any particular material. Different materials and different shapes and sizes will give different values, and we call that constant the letter R here. It's telling us something about the resistance to the flow of current. We measure it in units of ohms, and I'll write the word there for you. It's in units of ohms, thanks to George Ohm, who did a lot of investigations in this area. And we can rewrite that as now our potential V is our current I and our resistance R. There's a very important relationship between the potential difference, the current that flows, and the properties of the thing that the current is flowing through, this thing we call the resistance. And what we'll meet in the next topic is some really simple circuits where we'll see some examples of how that relationship between current, voltage and resistance plays out in many, many situations.